Hello again, and welcome back to another episode of Garage Science. So we're gonna create a coolant manifold for the Tormach, and it's gonna replace this coolant hose here. And so this hose works fine, and it definitely supplies enough coolant. The water pressure is good and everything else, but this flex hose is just so long, and because it extends out here, whenever you're trying to hit the part with a dead blow hammer, there's a tendency to try to bump this, and then you gotta fix it all. It's really annoying. So some of the nicer Tormach machines have a kind of wraparound coolant manifold that has nozzles that just spray directly onto the tool, and we're going to try and make something close to that. And so it's going to be a straight bar that comes across here. It's going to be higher up too, so that way, one, you get more of the downward spray angle, and also so that way there's plenty of room here to be able to wail on something with a dead blow hammer without bumping anything. And so and part of that's because the Z column's it's only got travel of 10 inches on the 440, so probably even the 770 doesn't have this sort of problem. But anyways, we're going to fix it for the 440 and try and make something a little nicer. It's going to have 4 nozzles instead of 2, and it's going to come out to right about here inside the enclosure, and so you should be able to get a pretty good angle from the back side and the front side, so that way you've got plenty of coolant on your piece. So we will give it a shot. Let's go. Alright, so we're gonna base this stock off. We basically got to cut it down to size. It's a little over 11 inches long. I'm using everything in millimeters for the cam, so it's 280 millimeters long, which is about 11 inches, and there's only a 10-inch work envelope for the PCNC 440. So we're going to do this side, then flip it, and then face off the other side until we trim it down to 280 millimeters, which I don't have a pair of calipers that big, so we're going to use a ruler, but that really shouldn't matter. This isn't a super precise part. But we are going to use a file that I just made up. Just hand wrote it in PathPilot, and I'll show you that in a minute, but we're going to test run it. The file is intended to be zeroed in the forward left bottom corner of the face that we're trying to face off. So we're going to already zeroed it here. We're going to run it here just to test run it before, make sure I didn't do anything stupid, and then we'll run it for real. Alright, so this is the PathPilot program. You can see in the preview for the toolpaths, we're just running a facing routine here. We're just gonna run in the Y direction, make one pass, come up, move back to Y0, come down again, right, change the depth, and do it again. It's very simple. But one thing I did want to point out is I started playing with this feature in PathPilot, which is that you can make your own variables, and so this is the format for that. So as I start trimming down the length of this, instead of finding the place in the G code everywhere where I change the X position, I just reference this variable, and I can change the whole thing at the top of the file for each time I'm going to trim this down. So it should be an easy way to cut this stock to size with reasonable accuracy without spending a lot of time doing silly minutia, and you know, it's less likely that we'll make a mistake that way. So here we go. So you notice I didn't get the whole face here, just because, you know, it's not a straight cut from the bandsaw. So we're going to offset the X0 now, and I'll probably change the depth from 0.1 millimeters to 0.2 and see if we can't get the rest of that face. But that was a solid run. So this is a good file to use for this. Alright, so I've ran it a couple of times now. It takes just under 2 minutes to run this, so you can do it pretty quick. But keeping the radial depth at 0.2 millimeters, I did change the last line. So I did have it going to the absolute coordinate x0, pulled that off, and made it go to the x depth of cut. So that way, when you finish, your x is at the depth of cut that you are currently at. So that way you can just zero that and have the offset for the next run. And so what you were having to do before is go to the offsets page, go to the worked offset, and manually add the radial depth of cut. So now you can just use a button to zero it each time. So we'll go ahead and run it again, and off we go. Alright, the stock is cut. I just compared these. They're the same length to within probably about 1/1000th of an inch. It's a very good match. So the length isn't a terribly critical dimension, but they need to be, obviously as close as possible so the screw holes line up. But 1/1000th isn't going to hurt that. So we're going to go ahead and get the cam posted and start making some real chips. Okay, so this is the cam, or I should say the CAD right now, for what we're going to try and make. So this is basically pretty simple assembly. It's just two parts. There's a lower part and an upper part, and so the rear part of the model is here, so this will be on the front end of the mill over here. So we'll have 4 nozzles, 1, 2, 3, 4, and the supply line for the coolant. And the manifold will get secured by M3 screws that are scattered across the top, and it'll bolt to the mill through more M3 threaded holes here, and that'll be the deal. So let's do this. We're gonna hide the top. So the coolant channel on the inside looks like this. So I've added a fillet to the inside corner, so that way it fits the ball mill that I'll be using, which is a 3/8 inch diameter ball mill. And then the holes are sized to accompany the tap for a 1/4 NPT thread size, which actually turns out to be a relatively large hole. But nevertheless, we'll do it. And then there's no gasket that's going to go on this. It's going to be a RTV like gasket maker for oil pans is what I'll use, and that should seal it pretty well. But there should be more than enough room in here, so all the nozzles should be well supplied with coolant. There shouldn't be very much restriction going down the manifold, so that way all the nozzles kind of supply the same amount of coolant flow. But let's go ahead and take a look at the cam files. So I have a separate cam file for each, the lower and the upper. So separate assembly. This is generally what I do is create a stock part, so that way you can assemble it with the stock and have all your references, etc., that you want to make, and it just kind of follows the part around if it ever gets changed. So I like that more than just a bounding box setup. So if you're not familiar with SolidWorks cam, then a lot of this might be new to you. I'm no cam expert, so feel free to leave your comments and opinions in the comments section. And yeah, I'm going to just kind of show you guys a few things. So the stock is sized to be the same length as the final part, and that's because the work envelope for the PCNC 440 is only 10 inches, and so whereas this part is 280 millimeters long, right, which is about 11 inches. So it's a little longer. I kind of wanted to do the part like that, so that way this would be a good kind of test to try and machine a first op in 2 pieces, because the part is larger than the work envelope, and just kind of see how that goes. So there's a few features here we're going to start with. So we'll start off with a center drill, and then we'll drill the holes for the nozzles. And you see these sketches I have here for these boxes here. These are not in the part files. This is in the assembly level, and so what we're going to use these as is avoidance area. So if I go down to the drill file, or let me pick one of these that has it. So this rough mill, to get the outside edge, right, there's an avoidance area here on the left that so basically the perimeter feature covers the entire size of the part. The avoidance feature just tells it, like, stay out of this area, so that way when it creates the tool path, it only does the first half, and then when we do the other half, then we'll just flip the avoidance area to be this side. It'll be the same cam feature, and it'll generate the tool path for the other half. So that actually is a process that works pretty well. So just show you the simulation for this part. We're not going to do details about the cam setup. Some of the things I'll mention, and you'll see in the video, is like I have this tool path that it's a volume mill tool path that cuts the top down to size, and it basically goes back and forth here. You'd kind of think that running sideways would be a little more efficient, which it would be, but doing a pocket in tool path in SolidWorks will basically mean that the tool path is going to cross the center back here, and when it does that, it's going to be cutting at a full radial depth of cut, which for a larger mill probably doesn't matter. It's going to be a 1/2 inch end mill, so it's not like the end mill is going to break, but there's not enough horsepower in a 440 to do a full slot on a 1/2 inch end mill. You will stall that spindle out faster than you can say oops. So we're just gonna nibble at it from the left side and work our way down. The other thing that I did was played with some of the 3D tool paths, but really it just ends up being one pass for the ball mill, which is the way I designed the CAD up. Yeah, so you guys will see that. So let's run the simulation so you can see it go. Now when the ball mill comes down and starts down here, you'll see that the so I'm cutting the entire channel out with the ball mill, and I don't know how well it'll end up coming through on the video, but it makes a racket. Ball mills, apparently, and this is my first time using a ball mill, by the way, ball mills don't seem to do end cutting very well. They'd much rather cut from the side than cut from the tip. And they, at least when I set this up, it made quite a racket, and it's pretty bad for the tool, I'm sure. So I'm going to avoid tool paths that utilize a ball mill to carve material out. And so let me give you the example that I have for the upper half, because it's relatively the same, but it's also a little different. And so you'll also see there's extra sketches here on the top for some hole features that I added. So essentially I drilled extra holes that don't actually go through the part, but it's material removal through the center to kind of limit the amount of full slotting that we end up doing. And then I also have a little bit of a extra tool path with a 1/4 inch end mill before we do the ball mill, to actually clear out as much material as we can before the ball mill comes in and finishes it up. So let's run that simulation. So the 1/4 inch end mill comes in, and then the ball mill comes in and gets the rest. So running this on the mill works way better. There's not nearly as much chatter. Still get a good surface finish. It does take longer, obviously, to run the extra tool paths, but it works really well. So the cool thing about doing the setup like this, so as soon as we go to the second part, which so now we're showing that, so you can see the coordinate system here now on the other corner, and and so it has all the same cam features, but because of the avoidance areas, all I had to do was swap that, and then you're ready to machine the other half. And there you go. That's how you get an 11-inch part out of a 10-inch work area. So we're gonna run this on the mill, and I think it's gonna go pretty well. And you guys can tell me what you think. If you got questions about specific things I did in the cam, leave them in the comments, and I'll try and get to them. And yeah, we'll keep going. Alright, so I forgot to get the camera set up before we started, but we're running the first part for the first operation. So the holes we're drilling right now are for the, really they're just entry holes, because we're going to bore out the holes for the nozzles with a 1/4-inch end mill. Look at that. That looks very good. Very satisfied. Alright, it's time to flip it around and do the other side. Okay, so this is the results of the first half. This is the lower half. Right, so we still got to tap these holes and tap these holes. But one thing I did want to cover, which I should have thought of this before, I thought I had accounted for it, but I guess not. Because we're doing two halves and getting these surfaces to line up perfectly, you know, you gotta get your part positioning and probing correct. And I thought by making my Z0 on the second half, this surface, that would account for any differences in the levelness of the original stock when you flip it around and put it in the vise the other way. However, I wasn't really thinking about the variance in dimensions in the Y, basically on the width, and so there's actually, this surface actually meshes up perfectly, except there's a little lip on this surface, and so should have thought of that being a possibility, and I didn't, and so yeah, now there's a little lip there. Shouldn't be a big deal because we're going to put some RTV sealant on here to seal the two halves together, but it's not a good look. And so what we're doing now, what the mill's doing, is we're actually facing off the bottom like I should have done originally, so that way you know that you have a flat surface all the way across, no matter how you mount it in the vise. So yep, we'll get rolling on the second half here in a minute. Okay, so this is the prepped stock now to do the first operation. You'll notice the faced off area doesn't extend to the very edges of the piece, again because it's longer than the work area for the mill, so that's just what we're working with. And it doesn't matter though, because this portion will hang off the end of the vise, so really not concerned about it. But now we'll have a nice flat area to reference off of for both operations, for both parts of the first operation. Okay, that's the first part of Op 1 done. Looks pretty nice. I think the kind of machining technique I was trying with the ball mill worked out a lot better for this one. Got a very nice looking surface finish on the inside of the manifold. And we flip it, because the bottom surfaces was flattened with the 1/2" end mill beforehand, then it should mesh, I think, a lot better with this surface, but we'll give it a shot. Alright, she is done. The upper part of the manifold went pretty well, no major issues, but there's still just a little bit of a lip when it makes the transition, and so I'm not quite sure how to get it to not do that. I mean, it's maybe 1 to 2 thousandths of an inch. There's also a little bit of a line where the walls meet, so it's I don't know, not quite sure how to fully get rid of that, if you even can. But that's probably more to the point. If you're going to machine something in 2 steps like this, especially when you've got the same surface that you're trying to mesh with another, best that it not be a dimensionally important surface. So like I said, we're going to seal this with RTV when we put the 2 halves together, so this lip's not going to make a very big difference, but well, it's a lesson learned. It's good to know. So we're fixing to put these together now, the two halves for the manifold. So got the bottom and the top, and we're going to use a bunch of M3 screws and put it together. But we're also going to put it together with this RTV gasket maker. This is oil resistant Permatex sealant, and so this is actually for oil pans. So basically I just wanted to use a sealant that would definitely hold up long term with the cutting oil in the mill. I didn't want anything that would break down, and so this ought to last a good long time, probably even a little overkill. I have tapped the M3 holes here with a hand tap, and I've also already tapped the quarter NPT holes for the valves for the actual nozzles. So we're going to go ahead and put this together and see how it goes. Alright, so that's it. So we will put the valves here. It'll be a valve, 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 and then input hose from the coolant line, and then we're going to use an angle bracket to basically mount on the top there with these M3 holes I left myself on the top. So we'll mount it that way, and I'll show you guys how we mount it in the mill here in a second. So stick around, almost done. Now that we've got the two halves together, we can go ahead and put the valves on and the mounting hardware for the coolant hose. So we'll go ahead and just jump right into it. Now this is going to mount in the mill facing this way, so I want the valves to be on this side. So as we screw these in, I'm going to try and get the valves to end up facing that direction. So I probably took the thread or the tap a little further. So if you weren't aware, NPT threads taper towards the end, and so that's sort of a natural sealing feature of that thread design. So as these twist in, they should get harder to turn. But that's what creates the seal. Okay, and there we have it. So, see, we'll attach the flex hoses to each of these, and then you can see that I tapped the hole a little out of square for the hose adapter, but that's not going to affect anything, so that'll be fine. Almost there. Just got to paint up the bracket and put the bracket in there that's going to mount it. So I'll show you that in a second. Okay, so we got the brackets painted. Basically, this is just some carbon steel had around, and so we're going to use this angle iron that's going to clamp onto the top here, and then we're going to use the original bracket for the Tormach coolant bracket, and so that'll mount to here, and then this will actually mount it all to the mill spindle column, and so that's how we're going to put this together. And then this whole thing will bolt up into the mill. So we can go do that now. So now this whole thing will slide up in here. So there's a flat plate I welded onto here, and that basically is to sit up against the spindle column so that way it can't rotate where it's at right now. So vibrations and everything else like won't cause it to rotate. And there it is, ready to go. So I can put the hoses on. So this is a handy tool anytime you're putting hose like this together. So it does a pretty good job of just snapping things into place. And then you can get it installed here pretty easily too. It's very, very fast and easy. So I'll put the link for all these components in the video description. You guys can get these hoses and nozzles for yourself with those. There we go. Easy peasy. And so we'll wrap this one around here. And that should also keep it out of the way of the tool changer. Okay, we can fire her up. Here we go, the moment of truth. So coolant pump's on. There's one. There's two. He's a little high. Point him down. There you go. There's three. And there's four. Oh yeah. That's some serious coolant power there. And it's at a much higher pressure than it was before. Alright. I need to cut something now. One thing I do want to add is that there is a need to have a filter in the coolant tank for this, because the nozzles I'm using on this manifold are 16th inch diameter nozzles, and coolant tank comes with the Tormach is there's no real filter for the sub pump, and so any chips that get into the coolant tank are likely going to get sucked back up and run through the coolant nozzle, and so with the 16-inch nozzle that's just going to clog, so you really need a mesh filter in the coolant tank. Well everyone, that is it. Thanks for watching. Make sure you like and subscribe. Leave me a comment in the comment section and tell me what you think. Share it around on social media. If you've got a small mill like me, then these kind of problems can be big deals to solve. So definitely tell me what you think of this project in the comments, and we'll see you next time. Right?